Today we will solve the problem 3.15 and 3.16 of Griffith third edition Introduction to Quantum Mechanics. First we will see problem 3.15. Prove the famous your name uncertainty principle relating the uncertainty in position x, that is operator A is x here, to the uncertainty in energy, that is the operator is P in our case, which is equal to the operator P is equal to P squared over 2m plus V. We have to prove that sigma x into sigma h is equal to or greater than h cross over 2m modulus expectation value of p. And another question is for the stationary state, this does not tell you much. Why not? So we have to answer this question. First, we have to prove this, and we have to answer this question. First, let us prove that sigma x, sigma h is equal to or greater than h cross over 2m modulus the expectation value of p. From generalized uncertainty principle, we know that sigma a squared into sigma p squared is uh, sigma a squared multiplied by sigma p squared is equal to or greater than 1 over 2 I, the expectation value of commutation of operator A with operator P whole square. So here in our case, sigma x squared sigma h squared is equal to or greater than 1 over 2 I. Here A operator A is x and operator P is h. So the commutation of x with h, of course, the expectation value is there. What is the commutation of x with h is equal to x, h is equal to p squared over 2m plus v. Remember that we are going to calculate commutation of x with Hamiltonian, but v depends only on x. So x and x will commute, so this will be 0. Only thing is now this 1 over m we can take out 1 over 2m, and we have to find the commutation of x with p squared. We will do it now. Just now we have seen that the commutation of x with the Hamiltonian h is equal to 1 over 2m x commutation of x with p square. Using commutation relation, we can expand this commutator, that is 1 over 2m x commutation of x with p and p. What we are doing is we are taking p squared as p into p. So I am taking the right hand side p to the right hand side. Similarly, left hand side p, we are taking left hand side. So this will become 1 over 2m p, the commutation of x with p. So the commutation of x with p is equal to I h cross. And here also it is I h cross. Here you have P, here also you have P outside the commutator. So this can be written as 1 over 2m. 1 over 2m you can take as a common. Then here you have IH cross P, plus IH cross P. Second term also IH cross P. So this can be taken as 2IH cross P, 2IH cross P. So here 2 will get cancelled. So the commutation of x with h is equal to, in the numerator you have I h cross, in the denominator you have m. Of course, in the numerator you have p also. So we got the value for the commutation of x with the Hamiltonian, which is equal to I h cross m multiplied by p. Now, according to generalized uncertainty principle, sigma x squared into sigma h squared is equal to or greater than 1 over 2i, the expectation value of commutation of x with h. So we have seen the expectation value of commutation of x with h is equal to I h cross over m. Here we have to find the expectation value. So I h cross over m is a constant. So only a variable is p. So we have to calculate the expectation value of p. Of course, we have whole square. Here you can cancel this I with this I. So now what you will get in the denominator, numerator you have h cross, and in the denominator you have 2m. H cross over 2m, the expectation value of p whole square. Now what is sigma x and sigma h, which is greater than or equal to h cross over 2m, the modulus of expectation value of p, because we are taking square root. Why we are putting modulus is this is always a positive quantity, that is uncertainty is a positive quantity. So the next question is next question asked is, what will happen at stationary state? At stationary state, the sigma h, that is Hamiltonian, that is standard deviation of Hamiltonian is 0, because it's a stationary, it has a fixed value of kinetic energy, that is kinetic energy and potential energy is 0. Then same is with expectation value of p, which is also equal to 0. If we apply this here in this expression, sigma x sigma h is equal to sigma, since sigma h is 0, the right hand side is 0, sorry, left hand side is 0, and sigma expectation value of p is equal to 0, because it's a stationary state, there is no momentum. So then naturally the right hand side also 0. So effectively at the stationary state, we cannot predict about sigma x and sigma h. So with this we will move on to next problem. Now we will see the problem 3.16. The problem 3.16 is, so that two non-commuting operators cannot have a complete set of common eigenfunction. The hint is so that the operator P and Q have a complete set of common eigenfunction, then the commutation of P with Q is uh, Q commutation of P with Q, which act on the some arbitrary function f must be equal to 0 for any function in Hilbert space. Let us say we have a function f of n. So when operator p act on f of n, you will get the eigenvalue lambda n with the eigenfunction f of f sub n. Then similarly, when the operator q act on f sub n, f n, then it gives you the eigenvalue un with the same function f sub n. So here it is very clear that f of f sub n is a common eigenfunction of p and q. So it's a common eigenfunction for q as well as p. So now we have to find the commutation of p with q which act on the some arbitrary function f, which is equal to the commutation of p with q is equal to pq minus qp, and the f of n, you take the linear combination of fn, f sub n. So summation that can be written as summation over n cn fn. Now you can separate this into two. PQ multiplied PQ act on the summation over NCN minus QP, which act on the function Fn. Of course, we have summation over n. Cn is the expansion coefficient, and Fn. So you take first case. What will happen when Q act on Fn? Q act on Fn, then it gives rise to lambda n, that is eigenvalue lambda n, uh, sorry, eigenvalue mu n, eigenvalue mu n, and you will get this. I will expand this. So when q act on f1, you will get p, because we are taking that q act on f of n, because you cannot change the operator just like that. So you have to follow the operator as given in the order. So when q act on f of n, it gives you the eigenfunction mu n, that is eigenfunction Cn is a constant you take out, and mu n fn. Now what will happen when p act on f of n? You will get this is equal to f Cn mu n are constant, you can take out. Then when p act on fn, you will get uh, eigenvalue lambda n. So this is equal to lambda n fn. So that's what I have written. Cn mu n lambda n fn. So similarly here, first P will act, so you will get lambda n. Then Q will act, for which you will get mu n. So the second term is after operator act on this, you will get summation over Cn lambda n mu n fn. So if you see the value of first and second, both are equal, but negative sign you have. So this and this will get cancelled. This is valid for any arbitrary function f sub n. So naturally, this is the complete set of complete set of eigenfunction, common eigenfunction in a Hilbert space. So we have proved this. Subscribe to my channel to get my latest videos, and join my channel to support its growth and enjoy the exclusive perks. Also use the thanks button to make one-time contribution and support my channel. Thank you very much.